In this module, we're going to look at the representation of floating point numbers and try to give a sense of how important it is to understand the internal representation of floating points compared to our conceptual model of real numbers, and how, in the right circumstances, the distinction between the two can really lead to important consequences. So first of all, let's look at the representation. So it really boils down to the traditional scientific notation. So for a number, instead of looking at the basic model where the period separate integer component to the decimals, one will look at representing a mantissa, in this case 101010, obviously in binary, and then multiply that by an exponent. Obviously, being in binary, this will be 2 to the power of a certain number. In the traditional decimal scientific notation, this would be 10 to the certain power. And so the main representations are single precision and double precision floating point numbers. There is a IEEE standardization for those. And again, that's important because otherwise in each machine you could have a different behavior. And in fact, you do. And so generally there is one bit that is being used to represent the sign, positive or negative. There is a few bits, 8 or 11, depending on the particular representation, devoted to the exponent. And then there is the fractional part, or better known as the mantissa, that in the float will be 23 bits, and in the double will be 52. Now, this particular number is not really important, but it's important to know there is one bit for the sign, fewer bits devoted to exponent, and a longer set to the mantissa. And in a way, the mantissa really dictates the degree of precision that the numbers really have as a potential representation. And I'll go in the detail actually for a single operation so that to see the difference and how important that is. So let's look at floating point versus fixed point. So the word floating really derived from the fact that the period really moves based on exponent. So if we think about a fixed point, and let's say we have an 8-bit representation, just to keep it simple for the examples. So we could say that there is a decimal point separating 3 bits before the decimal and 5 bits after the decimal. So in a way, it's conceptually similar to an integer, but it just there is a bit fixed on a particular location. When we go to floating point representation, then we have similarly a bit, obviously in both cases, for the sign. Then there are, say, 3 bits for the exponent and 4 bits for the mantissa. And so we want to understand how different is the behavior of those numbers, and how that could impact the computation that we perform. So let's look at what could be the smallest number that we represent in a fixed point representation. In this case, 3 plus 4 digits plus the sign. And so the largest modulo is 11111 in binary, and then we put the sign to be negative. And so if we translate this number to decimal, this would be almost minus 0.8. On the positive side, basically, we have the same modulo, just to flip the sign. And of course, then the decimal would be effectively the same, except the opposite number. Now, when we do calculations, what is the difference between two consecutive numbers, which really indicates how fine is the precision in the computation. So here we can look at, for example, number 1 as a reference. So we want to say, let's say we want to look at, we have number 1, we want to see how precise are the computation around 1. And so let's say we take 1, so in this case would be 0, 0, 1, 0, 0, 0. We look at the consecutive number and make the difference. And so 0, 0, 1 dot 0, 0, 0, 1 will be the next available number in this representation, right? There are no decimal points, decimal representation beyond this. And the difference between those two would be 0, 0, 0, 0.0001 in binary, which in decimal will be 00625. So now if we look at a different number, let's say number 4, and we want to test again what is the precision in the neighborhood of 4, we can do the same exercise. So number 4 is 100 in binary. We look at the next available number in this fixed point representation. That would be 1000001, again in binary. And now the difference between those two is again 0.0001, and so the precision is effectively the same. So in any for different values, the local precision of the computation is effectively the same. Now, the question is that true for floating points? So let's look at similar issues. So what would be the largest number we can represent? So here, now we have a shorter mantissa, if you will, obviously negative number, so 1.111, and then we have the largest possible exponents, 2 to 111. And then if we do the summation, minus 1 plus half, a quarter, and 8, so the different digits, times 2 to the 7. And so the smallest number is minus 240. If we look at what is the largest number, effectively it's the same computation, just the sign is being flipped. So here is positive, here is negative. And so same computation, effectively same summation, sign change. So the range of numbers is symmetric, but notice how in one case it's a very small number, this can be much larger. And so this is all good, and that's in some sense why often people prefer floating point numbers, because the range of value they can represent is much larger. Is there any consequence to that? And that can be seen in the precision of computation. So for example, let's look again of the precision around the unit. So let's say I have a number represented as a 1. So in this representation, that would be 10002 to the 0 exponent. So again, we have fewer precision. This is positive. We look at the next number, so we turn this bit into 1. So 1001 binary, 2 to the 0, minus this number. And basically, the variation in value is 0.001 and is 0.0625 in decimal. So for number 1, actually the precision is the same as the fixed point in this particular case. So let's look at then a value of 4 and look at whether the precision in that neighborhood is the same. So number 4 would be 100, at this point 2 to the 2nd power. And so again, the mantissa is the same, but the exponent is different. Now we increment by 1 in the lowest possible bit to look at the next available number, so 1.001 2 to the 2nd power. We do the difference, and so this is going to give us the local precision. Now 0.001 power 2 now goes actually to 0.1 in binary without exponent, so we have to multiply by 2 to the 2nd, 4. And so effectively, the difference between those, the minimum difference between consecutive number, now it's 0.5. So you see that for a certain value, the precision, the local precision can be much finer, and for larger number, the precision it's much coarser, and so that allows to have this wider range of numbers, but with a cost of a representation that is not uniform. And so that's why one has to be very careful in using those numbers. Kind of visually, we can look at this from the perspective of how the numbers are distributed. And so as we were seeing, so here we have the numbers in single precision and double precision. And so here the precision, a low number means much finer precision. So the computation are more precise. And then in both cases, as the numbers get larger, the precision get coarser, so consequently number have different range of value. If we look at integer distributed along the x-axis, so one can think about how many floating point numbers exist between two consecutive numbers. And so here you see for numbers really close to the zero, there is really lots of numbers. And then as the numbers get larger and larger, the number of elements, the number of floating point numbers in between two consecutive integers gets lower and lower as the computation increases in range of value, in absolute value. So this really creates a very biased way of computing that can have actually very serious consequences. If you are far enough from the limit of the precision, this is not necessarily a concern, but especially in engineering computations that have high stakes, like the structural strength of a bridge or things in that space, if you're hitting the limits, that could have catastrophic consequences. In particular, this is an example, a real example that happened during certain military operations, and in particular, the Patriot missiles launching system was computing targets in a certain way, and just a precision issue created a problem that actually ended up having really catastrophic consequences. In particular, the problem was that the computation in the system internal clock that was used to compute the trajectory was multiplied by 1/10 to shift the time from decimals to seconds. And this calculation was performed with register with a limited precision. Now, what's important is that to see what happens when you represent things in this level of precision and you don't think carefully of the precision of the registers that are using those numbers. So I'm going to look at this from the perspective of computations and show how really it's not easy, it's not intuitive to think about what numbers really exist in a certain space, especially binary versus decimal. So I'm opening in Visual Studio a Python interpreter. And so let's say we take a variable. So here just kept some examples. So a equal 1. And now I look at printing the value with a very detailed precision. Otherwise, I would not. So if I simply say a, I get a simple 1. So here I want to have the precise representation with all the digits after that. So for a equal 1, I get 1.000, and 1 is equally represented in decimal and binary. If I go up to a equal 10, you can see the precision is lost. I can even go to 100, and I still have very precise information. So it gives the impression that, as you can do in decimal, you can move the the precision. But now if I go down and I turn A from 1 to 0.1 and I print it normally, I get the impression everything is fine. If I go and print very much in detail, I can see that actually the real value that got memorized is 0.1 and a good number of 0, and then 5511, and so on and so forth. So the interesting fact that is not intuitive, that in floating point representation 0.1 literally does not exist, and so when A is assigned to 0.1, it gets assigned to the closest number, closest binary number in floating point representation to that particular value. And then normally when it's printed, it's rounded back up, so you don't notice that a variation like this happen. And in the case showing before, we're talking about a very precise trajectory being computed, and now switching from an actual 0.1 towards 0.1 and then additional digit created a very catastrophic consequences. Practically in binary, just to get a sense, 0.1 in decimal would become this very, very long sequence of digits, basically, for all practical purposes, never ending. And so this is the part that one has to be very aware of. Here in the slides, I put the example that around there in Python, just if people want to try themselves. In this case, I'm using Python just because, being an interpreter, it's very easy to type things as a calculator, but obviously you're welcome and in fact encouraged to try this in C++. So this is not really a problem associated with the language, but is really an internal problem associated with the binary representation in a computer, and that emerges very quickly if you do high precision computation, either in C++ or in Python. Thank you very much.